We are starting a new topic, and that is soil strength. And we already covered this last semester, so I'm going to go through this pretty quickly. Put it this way: we covered it a little bit last semester. So this semester we are going to go into it in more detail. But as a review, I am going to redo what we did last semester. So bear with me. It's going to be a little bit repetitive and that sort of thing, but I just want to make the points, refresh your memory, and then go farther with it. So if you remember, when we have soil strength, one way we are concerned about it is that I have a structure here that is standing up vertically, and what we're afraid of is that the structure is going to rotate and basically tip over. And what's happening underground that you really can't see when a building or structure does this is that we get a shear failure down here underneath the structure. And that takes place, it's approximately a circular shape, or a portion of a circle. And when we look at the stresses on that shear surface underneath the structure, so here's my structure, what we do is we take one way to do it, take moments about that point, and the forces that we are looking at when we do that is I am taking moments of this point. Well, I have a weight to the structure that is causing the structure to move, in this case, in a counterclockwise direction. And then what is resisting that is that we have shear stresses in a clockwise direction here that resist it. And we want the potential shear stresses that we can develop along here to be greater than, to cause a moment that is greater than the moment caused by the weight, and by a factor of safety amount. And so what we are concerned about is what are the potential shear stresses we can develop. In other words, and those shear stresses that we can develop are the shear strength of the soil, So the resistance is basically the soil shear strength. And when we say soil strength, that's an abbreviation for soil shear strength. In other words, if you remember, when we're talking about, by contrast, steel, if somebody asks you what is the strength of the steel, you give that person the steel tensile strength. Why? Because that's the way we refer to steel strength. Well, with soils, there is no tensile strength of the soil, and so we don't really get tensile stresses in soil. What we're always talking about, if somebody asks you what is the soil strength, they want to know what is the soil shear strength. So this is a picture here of exactly what we're talking about. This is the classic bearing capacity. We call it bearing capacity failure. This is referred to as a bearing capacity failure. And you can't really see what's going on underground in this picture, but it's approximately that. So, okay, so like I say, we covered this last semester. You can review what we did last time. I'm repeating a little bit of it here. You can look at YouTube videos from April 25th, 2020, 9 a.m., 9:30 a.m. So go ahead and re-watch those videos if you like. I'm going to repeat some of it here, but more quickly. Okay, so like I say, soil strength is shear strength, and there are two kinds of shear strength. There's drained strength and there's undrained strength. And there are two kinds of loading in situ that we do. There's drained loading and there's undrained loading. So, in a nutshell, if we have drained loading in situ, in other words, in the field, and I will define these terms and what we mean by them. If I have drained loading in situ, then we use drain strength in our analyses. If we have undrained loading in situ, we use undrained strength in our analyses. Fundamental to this is this concept, and the new concept is that shear stress can cause excess pore pressure. So we've talked a lot about excess pore pressure last semester, and we always talked about it, well, at the beginning, or through most of the semester, we talked about the excess pore pressure generated by, for instance, placing a fill on top of the soil, and we're compressing the soil. We get an excess pore pressure due to the weight of that fill, which is basically what we just got done doing. But now I just want to explain again briefly why shear stress can cause an excess pore pressure. So how does that happen? For instance, here I have my soil particles in this manner. Notice that I have I've got a saturated soil, and I have a good bit of void space there. And what can occur is that if I create a shear stress in this manner by pushing in one direction at the top and another direction at the bottom, so pushing to the left at the top, pushing to the right at the top and pushing to the left at the bottom, in a sense, what happens is that when the particles move, the particles fall into or move into the voids, and when they move into the voids, they compress the water. So the water originally starts out a lot of void space. It goes down to little void space. Well, what happens? The particle going into the void presses the water, and the water gets squeezed, and it creates excess pore pressure. We use these words drained and undrained, and I'm just going to tell you up front that drained loading is slow loading. Undrained loading is fast loading. Now, we use those terms. When I say drained and undrained, what happens is that in this situation, when the water gets pressurized due to the particles moving into those voids, well, if the water is pressurized, it wants to go somewhere. It wants to go where the pressure is low. So, and the amount of time that it takes for that pressurized water to go to a new space where the pressure is low is critical. And in other words, if you just look at it this way, if it's a gravel, the water moves very quickly through gravel. So if the water is pressurized in gravel, then it very quickly the water moves very quickly into a place where the water pressure is low, and then basically it all equalizes at a low pressure. And so in a gravel, the excess pore pressures dissipate very quickly. These excess pore pressures will dissipate very quickly. If it's a clay, then we know that water moves very slowly through clay, so if we get these excess pore pressures, then they dissipate very slowly. Okay, so those are the concepts, and that's why we refer to a very slow loading. We call it a drained loading. In other words, if we load the soil very slowly, then it may happen that we load it so slowly that these excess pore pressures generated by the shear stresses will dissipate during the loading process. On the other hand, if we load it fast, what we're going to find is that the loading is so fast that the excess pore pressures can't dissipate during the loading. And so we have excess pore pressures building up before they're built up and remain there after the loading is finished, in a sense. Okay, so in the lab, when we run a strength test, we'll run the strength test, and sometimes if we apply the load rapidly, we are running an undrained test. And at failure, we get the undrained soil shear strength. So if I do everything fast in the lab, undrained loading is fast, so I do undrained loading in the lab, meaning loading it rapidly, we will get the undrained soil shear strength. Drained loading is slow. And so if we apply the load slowly in the lab, we're running a drain test, and we get the drained soil shear strength. So undrained loading is fast, drained loading is slow. And, okay, this is my structure, for instance. Again, what we're looking at is even though I put on a vertical load here, I am creating shear stresses in the soil. I need shear resistance to prevent this from happening. So building a structure creates shear stresses. And so, in a sense, the process of building the structure, which we may do quickly, may not do very quickly, depending on the situation, because we can't build this structure instantaneously. We may be loading the soil in an undrained manner, or we may be doing it in a drained manner. We have to look at the situation. Depends on how fast we're building the building. It also depends on the soil type, because I gave you two different situations, one with gravel and one with clay. So what this figure illustrates, these two figures illustrate, is that we are generating shear stresses in the ground even when we build a structure, when it's not quite so obvious that that's what we're doing. How fast is fast? Well, it depends on the soil type, as I said. It depends on how fast excess pore pressures can dissipate. Well, as we said, sand and gravel. Well, sand and gravel, for sand and gravel, the excess pore pressures dissipate very quickly. Now, so in order to generate a very quick load in sand or gravel, generally, we use an earthquake load will generate undrained loading or rapid loading. So you have to feel comfortable with this, that undrained loading is fast, drained loading is slow, and so earthquake loading is very fast. I mean, and one cycle of a seismic wave is approximately 1 second. So 1 second, during that 1 second, even in sand or gravel, you're not necessarily going to get excess pore pressure dissipation in that 1 second. So that would be, an earthquake loading would typically be an undrained loading for sand and gravel. But if we're not doing so, we're going to set aside an earthquake loading because we're not going to analyze that in this class. So what we're going to find then is if we simply build a structure that's going to be drained loading, because it'll take us, maybe a year or two to build our structure. Well, that is such a slow loading for sand and gravel that it's considered a drained loading, and therefore we use drained strength. So we use the drained strength for sand and gravel. So except for earthquakes, we're going to use drained loading and drained strengths for sand and gravels. And yeah, this is my illustration of an earthquake loading where the base rock moves, for instance, back and forth horizontally, creating a seismic wave that travels up to the ground surface. So that is an earthquake loading. We aren't going to look at the earthquake loading. So for this class, for sands and gravels, we're always going to be using drained loading and drained strengths. So we're going to be interested in the drained shear strength of our sands and gravels. Clay and silt, on the other hand, what do we find? Well, I mean, it's all relative, but we'll put some numbers on it. But for normal construction using clay and silt, we're going to be concerned with undrained loading and undrained strength for immediately after construction. In other words, even if we can build our structure in a couple years, even if it takes a couple years to build our structure, that is not long enough, a couple years, to dissipate the excess pore pressures. We've put numbers on it. It may take 20 years to dissipate our excess pore pressures when we did our settlement analyses and things like that. So it takes many, many years. It can take many, many years for the excess pore pressures to dissipate in clay and silt. So we're going to be using undrained strengths for our analysis of what happens right after the structure is completed. On the other hand, well, we're going to use drained strength for a long time after construction. So in other words, suppose our structure is going to be there for 50 years or so. Then, because it's going to be there for 50 years, we want to make sure that even after the pore pressures have dissipated, that the building is still stable. So we will use the drain strength for a long time after construction. So in other words, when we're doing any construction on clay and silt, we're usually going to be doing both an undrained loading and undrained strength analysis and a drain strength and drained loading analysis, because it has both. So for sand and gravel, we're going to use drained. For clay and silt, we're going to use both undrained and drained. Most of the time, that's the way we're going to look at it. So, okay, we have an acronym. I like to use this acronym that is handy to keep it for you to remember. It's EDS tough. EDS tough. EDS-TUF. What does EDS stand for? Effective, drained, slow. So those three go together. What does that mean? That means that when we have slow loading, the situation is drained, and we use effective stresses. We do what's called an effective stress analysis. I'll explain that later. Tough, TUF, total, undrained, fast. And what is that? That means that when we have fast loading, our situation is undrained, and we are going to be using total stresses, not effective stresses, in our analysis. So, and again, I will explain those. But so remember this acronym. EDS, tough. If you remember that, then you're going to be able to group these three together, effective, drain, slow, and group those three together, total, undrained, fast. We talked about the direct shear test or shear box, and just as a refresher, this is what it looks like. We have a top half of the box, a bottom half of the box, and in between there is a gap between the top half and the bottom half of the box. We apply a vertical load, which is constant. We hold that constant through the test. We apply a horizontal load, and we increase that horizontal load until we get failure. And so it looks like this. So here we have, in this particular test, we have the bottom half fixed, it doesn't move. The top half moves. And in the process, we create a shear plane right through the middle of the structure, and that's the middle of the box. And that, we're going to say we have that shear plane there, and we are going to measure that deformation delta, and we get, like I said, we increase this F until we get failure. So we plot that up. As we increase F, we increase delta. So we get an increase. We hit a peak. We get an F max for a given P. And we can get the strength from that F max, for instance. In more detail, we have the box, the top half of the box. Often we have this top plate that's separate from the sides. When we look at it in plan view, we have a cross-sectional area of the soil. These dots are the soil here. The dots in all of this are the soil. And we have a cross-sectional area of the soil so that we can get stresses. So force over area gives us stress, so the shear stress is going to be the F over the cross-sectional area. And we're going to call it tau FF, where FF means the FF means at failure on the failure shear plane. So the FF, again, FF is at failure on the failure plane. At failure on the failure plane. So here's my failure plane. This is at failure. We're at the peak there. We're going to use the peak. And so again, force over area gives us stress. We're going to use tau for shear stress, as we always do. Sigma is normal stress, as we always do. What is the sigma? Well, we have the P, there's my load, P, over the cross-sectional area. And then we keep P constant in this test. So sigma FF is going to be P over the cross-sectional area. And as we said, for sand and gravel, the lab test is a drain test because the pore pressures dissipate very quickly. And so we end up basically with a UXS equals 0 because as soon as we start to build up the excess pore pressures, they dissipate. So even if we're running a saturated sand, we're going to have a UXS equals 0 simply because they dissipate so quickly. And like I say, we're not going to run an earthquake simulation on the sand or gravel. So sand and gravel become quite straightforward. We run our test, we plot F and delta for a given P, and we get what looks like a stress strain curve. We pick off the F max, and we convert this. These are forces and displacements, so force F, displacement. We're going to convert those to tau and gamma. Now gamma is not density in this case. So we're using the symbol gamma, not density. So don't get fooled by that. In this case, the gamma is, if you remember, we've used gamma for shear strain in structural engineering, and we stick with that terminology. So we get a plot of, it's a stress strain plot. but in this case we have shear stress and shear strain, not normal stress, not sigma and epsilon. So it looks like a stress strain curve, and we get our tau FF at the peak. So it's like our F max comes from our F max. So we get our tau FF, which is important to us. We then, if you remember your Mohr circle, which is tau sigma, and let's go, remember this is our drained. Remember, this is drained, both in the load and in the strength. And so we get the drained loading and drained strength. So if you remember what our acronym was for drained, so we have EDS, tough. What is it? So we have EDS and we have tough. So what are we talking about here? Well, we don't have tough because we have drained, effective, drained, slow. So we are in the EDS. That is what we're talking about here, EDS, effective, drain, slow. We're not talking about tough. So effective, drain, slow means that we are going to plot, long story, we plot effective stresses down here. It's one of the things that we're going to do EDS, effective, drain, slow. We're doing effective stress analysis. So we put in effective stress for our sigma. So we use sigma prime. So if you remember the axes in the Mohr circle, we have sigma, it was sigma and tau, but we're using sigma prime. Okay, so we're going to plot this result from our test here. There's our test result. That's our test result. And what we're going to do is plot that test result onto our Mohr diagram. And so, like I said, we're going to use effective stress here. So we're going, now what do we know here for a given sigma FF? Well, our life is easy in a sense because what do I know? Since UXS equals 0 and we have a small sample, a short sample, small sample, whatever, then that means that U equals 0. The pore pressure is equal to 0. And if pore pressure equals 0, that means that sigma is equal to sigma prime. So for our test result, this is quite straightforward. We in our test result, sigma and sigma prime are equal. And so we end up having, we just simply, we would take our sigma FF, and what we see is U equals 0, sigma prime equals sigma minus U, sigma prime equals sigma, and so therefore sigma prime is simply P over the cross-sectional area. So we take sigma prime, which is still sigma in this particular case, and tau FF, so we plot that value, we plot that value onto our plot, 1 point there, and then we draw a line from the origin through that point, and that gives us our failure envelope. And if you remember how we did this, this was the no failure region, so we created 2 regions, one with no failure, one with failure, and so once we get our test results, we look for the stresses in the field. If our stresses in the field are down in here, then we don't have failure. If our stresses in the field are up in here, then we do have failure. In other words, if the stresses in the sandy soil or the gravelly soil are down here, it's no failure. If the stresses in our sandy soil or gravelly soil are up there, then we do have failure. So we take our test result from the lab, and then we do our analysis of what's going on in the field, figure out where we are at. And we call this angle for that line the friction angle, or the angle of internal friction, phi prime. You need to put in the prime, phi prime. And we can get our coefficient of friction, basically. If you remember, F is equal to mu times n, and it works out that mu is simply the tangent of phi prime. So in a sense, we get our friction coefficient. We don't quite use it in that manner, but that is the basic concept. And so this is a very important page for you. This page shows the three representations of the soil strength for different soils and conditions. You should memorize the three plots. You need to memorize these. You need to know these. And we have sand, we have clay. We have clay drained and silt. So let's do it this way. So we group sand and gravel, and we group clay and silt. That's the first thing. So I'm going to quite often just refer to one, or sand and clay, and you should know that that could be gravel and silt. Or, so sand and gravel grouped together, clay and silt grouped together. So, but now I'm just going to use sand and clay. So up here is sand drained, clay drained, clay undrained. And these are what the failure envelopes look like. We have sand drained, goes through the origin. The angle is phi prime. For clay drained, the line doesn't go through the origin. So we have a C prime. The angle is phi prime. So we have a C prime and phi prime there. For clay undrained, we have a line, it's horizontal. So the angle would be 0, and then we call the intercept C or SU. SU standing for undrained shear strength. What you need to know, so you need to know this. Sand drained through the origin at an angle. Clay drained, not through the origin, at an angle and an intercept. Clay undrained, horizontal, intercept is C or SU. And we should note that's C prime. And again, Ed's tough. You need to have an understanding of that. So know this page. You need to have this in your mind when we solve a lot of problems. If you forget it, you're going to be lost. So this is the same thing. You can go over this. 2 kinds of soil shear strength, drained and undrained. 2 kinds of loading, drained and undrained. And when we have drained loading in the field, we use drained strengths in our analyses. When we have undrained loading in the field, we use undrained strengths in our analyses. So we have to, there's our Ed's tough. We have to decide whether or not, or what we have in the field. So, and like we said, the U excess determines if we have drained or undrained during loading. And as we said, if U excess equals 0, we have drained loading. If U excess does not equal 0, we have undrained loading. And the U excess is caused by the shear stresses, which causes the particles to fall into the voids and cause excess pore pressure. So let's just put some numbers on it for this situation, for instance. Okay, so I'm going to construct a dam, for instance, and I've got clay. I've got 10 meters of clay. Here's my dam. Here's my C sub V for that clay. The dam is, for instance, 20 meters high. And what we are doing is we build the dam in layers. So, it's an earth dam. So we're piling dirt up, basically. And what we're worried about, for instance, is a failure taking place along this shear plane. And what occurs? Well, I've got, here's my shear plane. And on that shear plane, what? We always have a normal and a shear. When we make a cut through soils, we have normal, shear, normal, shear. It's like friction. If you remember the way we analyzed friction in your statics class, we had a normal and a friction. Well, here we call it normal and shear, but it's basically friction. And so what we want to make sure that the moment, so we have a moment that is basically caused by the weight of the dam, and so that gives me, again, it gives me a counterclockwise moment about that point, for instance. It's not exactly analyzed like this, but approximately. That moment is countered by the clockwise moment of the shear strength of the soil. So I'm taking moments about that point, and I get a clockwise moment. And in order to determine this clockwise moment, I have to get the shear stress at failure on the failure plane, which is the shear strength, the tau FF. I need that tau FF. What will be that? And okay, so we want to get this tau FF, but we need to ask ourselves, well, do we want the tau FF drained, or do we want the tau FF undrained? And what we're saying is it's going to take us 10 years to build this dam. So I've got a C sub V of 20 square meters per year. And so, okay, so here's the solution. Is the loading drained or undrained? Well, is the loading slow? If it's slow, it's sorry. If it's slow, it's drained. If it's fast, it's undrained. So what we need to do is figure out how fast these excess pore pressures in this dam are going to dissipate. Well, we can go back to our T is equal to C sub VT over HDR squared. So, well, if you look at our chart, for 95% consolidation, we get approximately a T approximately equal to 1, capital T equal to 1. If you remember how, let's look at this. Let's go back to our, we can go back to this chart here. It's approximate, but if you look closely here, we have T equals 1. Well, if I get T equals 1, I'm down there. Yeah, pretty much, this is just a rule of thumb in a way. If I'm way down in there, I say, all the pore pressures are pretty much dissipated. And that's at a T, capital T, of about 1. So 1 is an easy number to take. It could be 1.1, but it's approximate. So we take T approximately equal to 1, so then I put in T equals 1 here. So I put in T equals 1. I take my C sub V as 20. My HDR, well, is it single or double drainage? Well, it's single drainage because I have rock underneath there. So I have HDR is H, which is 10. And then I have small t. I solve for small t, I get t equals 5 years. So I get 95% dissipation and 95% consolidation, dissipation in 5 years. Well, I built it in 10 years. So what do we see? That 5 years is less than 10 years. And so we would call that a drained loading. In other words, our excess pore pressures will be dissipated before the loading is complete. So approximately, like I say, this is just a rule of thumb on how you can figure this out. It looks like this is going to be approximately drained loading. So because the pore pressure dissipation is faster than the loading. I get pore pressure dissipation in 5 years, my loading is 10 years. That means that I have drained loading for this. So I have drained loading, I use drain strengths. So these tau FFs, what am I interested in? I'm interested in the drain strengths of these along this failure plane. And what are the drain strengths? Well, you need to remember I have sigma prime, I have tau, and then I use that failure envelope there, where that is C prime, and that is phi prime. So that's what you learn from that, and that tells you which failure envelope to use. I need to use the drained strength failure envelope to analyze this. And okay, we've covered this through the failure envelope and the ED's tough, and you can pause the video and go through this, but it's what I've just gone through. All right, let me do this problem and then I'll stop. So here's a little example, which is find the force F at failure if phi prime is 32 degrees for a sand, a dry sand. And I've given you the cross-sectional area, I've given you the P, 0.05 kilonewtons, cross-sectional area 0.001 square meters. And so we have our P is 0.5 kilonewtons, and that means that my P over A is 0.05 or is 50 kilopascals. And my question is, what is F over A? What is my tau FF here? I've been given that the phi prime is 32 degrees. Okay, so this is, we have our, in stresses, P over A, F over A acting. It looks like the little square that we analyzed with Moore's circle. All right, so our solution, what are we going to do? We're going to draw this failure envelope for sand. What does the failure envelope for sand look like? Well, we know it goes through the origin. We have a straight line there. The friction angle phi prime is 32 degrees because we were given that 32 degrees. And what we have is that, what do we know? Just by simple geometry, that tau is sigma prime tangent for this line here. Tau is sigma prime tangent phi prime. That's just basically trigonometry. And so if my sigma prime is 50 kilopascals, my phi prime is 32 degrees. So we get that 50 tangent 32 degrees is 31.2 kilopascals. So what we're trying to find here, I'm at 50 kilopascals. I want to find what is that point on the failure line. And so what we get is, that tau is 31.2. That means that value is 31.2. That's the y coordinate of that point. And therefore, that gives me tau. Well, tau is F over A. And so we get that F is tau times A, which is 0.0312 kilonewtons, which means that when I plot my F versus delta, I'm going to hit 0.0312 at the peak. It's going to look something like that, right there at that peak. So in this particular case, this is sort of a backward problem to a certain extent. We know that phi prime is 32, and we're trying to get the F at failure. Usually when you're running a test, we do the opposite, is that we, let me just add that so that we know that tau is equal to F over A. So typically when we run the test, we're trying to find the phi prime. Here I've asked the question in reverse. Okay, we'll stop there.